review DC circuit. So in Chinese, 直流电路. DC means 直流, circuit is 电路. Another terminology, terminal voltage. 终端电压. So terminal is 终端, voltage is 电压. Little r, it's called internal voltage. So inside the battery, 内阻, 内阻. In series, it's called 串联, 串联. In parallel, in Chinese, it's called 并联. Okay, all right. So a DC battery or source is talking about this here. One long, one short, so plus minus. You can call that a DC battery or a source or electromotive force. So EMF. Or you can write it as epsilon. This one is epsilon. Epsilon in Greek letter. So if you look at the battery like this, you look at the two terminal, positive terminal, negative terminal. So positive terminal A, negative terminal B. So if we write VAB as VA minus VB, so VA is slightly higher electric potential and B is lower electric potential. So then between A and B, you will be adding, you will be going from this way to this way, you'll be adding this epsilon here. So this one is referring to this epsilon. And then you will minus I. So I is going this way, I is going that way there. I times the little r. So that's according to the Ohm's law. So epsilon minus IR will become, when you go from this to here, you increase by epsilon and then you reduce by I times R because you're dissipating energy there. So that's called terminal voltage and VA minus VB. It's equal to epsilon minus IR. Or you can look at a circuit like this. So let's look at just this part here, A and B, and I is going this way. So if you're going from here, so this is minus and this is positive, going from here to here, you would subtract the minus IR and then plus the epsilon. So A will be higher than B because this battery will have more voltage difference than the voltage dissipation in this R area. So epsilon minus IR will still be positive. And that is the difference from B to A, right? So A will be higher than B. Okay, so in series, if you have resistor, that's like this and that. So let's say you have two of them, R1, R2. Then your equivalent, R EQ is equivalent, is equal to R1 plus R2. If you have three of them, this is 2, R3, then you will then add another one. And when you are in parallel, then you will be connecting this way, like that, that, and that. So that's 1, 2, 3, R1, R2, R3. So then the equivalent of this will be like that, and this R equivalent is equal to 1 over R equivalent is equal to the sum of 1 over R1 plus 1 over R2 plus 1 over R3, right? So that is the in series and parallel. So when you are in series, basically you're making the resistor longer and longer, right? You're making this longer. You're making the resistor longer, right? Remember, resistance is equal to ZO and then L divided by A. So if you make it longer, you will increase the resistor. And when you're in parallel, you're basically increasing the area, right? So you have 1 path to go, 2 paths to go, and 3 paths to go. So now you have 1 area, 2 areas, 3 area. When the current comes over here, he has multiple directions to go. You have more path, 更多的路径 in Chinese, right? So then your A increase. In this case, you basically your A increase, and the A increase R will reduce. So that's what it goes. So resistance decrease when they are in parallel. The resistance, the equivalent resistance increase when they are in series. Okay, all right. So the brightness of a light bulb, it's the intensity that we're talking about. Intensity is defined as power divided by area, right? So if you have a light bulb here, and you're looking at this sphere, right? This surface area here. If your R is the same, you're always looking at this distance here, then this A is the same, right? Your surface area is the same. So then your brightness is then proportional to power if A is fixed, okay? All right, number 6, Kirchhoff first rule. So Kirchhoff first rule, the first one is junction rule. So what does that mean? If you come here and then you spread or split, right, into 2 paths. And this one here is I1, and this is I2, and let's say you have I3 coming in, okay? You can add more, let's say you have I4 coming in, right? I4 coming in. Then the entering is I3 plus I4, right? So it'll be I3 plus I4 will be equal to the exiting. The sum of it is I1 plus I2, right? You can add another one too, and it'll be here, and that's called that one I5. Be adding this 2, I5, right? So entering sum equal to exiting sum. It's also called current rule, right? So it's all talking about current entering and exiting a junction. And a junction is right there. That's a junction right there. So you have multiple line that's joined together. It's called a junction. So Kirchhoff's first rule is due to the charge conservation. As you can see, I is equal to charge divided by time. And if time is the same, then when the I coming in is equal to I going out, it's basically saying the charge coming in is equal to the charge going out, right? So this is in and that's out. So it's called charge conservation rule, or the law of conservation of charge. Number 7, Kirchhoff's second rule is a voltage rule. So if we have, let's say we have a circuit like this, one loop, and let's go another loop, and you have a battery here and another resistor there, for example. So now your current goes this way, right? Now you can define 2 loops here. One loop goes like this. It goes, come over here, go around to the lower path, and then come, right? So that's your loop 1. So that's your loop 1. Okay? And then loop 2, here goes your loop 2. So loop 2 goes right there. You go this way, and you go up this way, the upper loop. And you go this way, you go that way, and then you go around, right? So that's your second loop. That's your loop 2. Okay? So you can write the second rule around a loop, okay? Any loop, you pick any loop. So it can be loop 1 or loop 2 here, right? And then you're adding all the voltage drop and the increase together, starting from 1 point. So let's say if we're starting at, let's get the point right there. Say if you start from here, for example, right? If you start from here, then you're adding this voltage here, and then you come over here, you'll reduce, right? And then you come over here, you'll reduce again, right? So if you do the low loop, you will have epsilon, right? Plus, and you minus, let's say, let's call this one R1, minus I1, right? This is I1 right there. This one is I1, right? I1, R1, and then minus, and this one here is I1, I2, so this one will be I there, for example, and it'll be minus I times, let's say, the little r, right? Minus I times the little r, and then you come back to this point again, so then that's equal to 0. So that's how you apply the second rule around any loop. You can do the similar things for the loop 2, okay? So loop 2 right there, you can write it the same thing. So then you then write plus epsilon, and then minus, and let's call that one I2, okay? And then this one is called R2. So minus I2, R2, and then minus, and come over here, minus R times I. So this is I2, but that's I, and that's equal to 0, back to here. So that's how you write the second rule for the Kirchhoff. And this is a law of conservation of energy, right? As you can see, the electric potential is energy per charge. So then when you go around, you come back to the same point, and you did not increase any energy, right? You go around, you increase it, but then you reduce it, and you come back the same energy here. So that's called the energy conservation per charge, okay? Right, so that's so far, and we're going to continue reviewing the Kirchhoff rule. We got a little bit more convention for Kirchhoff loop rule. Yeah. Junction rule, it's more straightforward. Loop rule in complicated situation can be a little tricky. So here we define convention for the loop rule. So for example, in this circuit here, we have 1, 2, 3 battery, and we have 3 resistors. So when we draw the red loop here for 1, so the loop 1 is going counterclockwise. So loop 1 is counterclockwise. This is just arbitrary. So you are assuming that's your loop, okay? And then your loop 2, you also join in counterclockwise. So you can do it the other way too. And the result should be the same. Now, when you do this, and I put a dot there, meaning I'm going to start from there. So from here to here, negative to positive, I need to add 10. So that's why I add 10 right there. And then continue. Now I come to the R2, because the currents through R2 is I1 here. And I1 is the same direction as my loop direction. So it will be minus. So then I have minus I1 times R2. And then continue. Oh, I didn't add this one here. Continue here. This one here, the current in the loop, the same direction. So I need to have a minus I2 R4. Added right there. And then continue for the battery, because I'm going from positive to negative. Right here, I'm going from negative to positive. So that's an add. But when I go from positive to negative, that's a minus. So minus 5 volts. So I have minus 5. And I'll continue going this way now. Now this is, the loop is going to the left. And the current also going to the left. So both are same direction. So that's a minus. So minus I1 R1. And now I'm back to the same point. So equal to 0. Okay. So for loop 2, I'm looking at this counterclockwise. You can see my I3 is the same direction as my loop direction. But my I2 is opposite direction of my loop direction. Okay, so for loop 2, if I'm starting from here, I put a dot right there. So go from minus to positive. So that's add 5, plus 5. And then this one here is opposite direction. The current direction is opposite to the loop direction. The loop is going down, but the current I2 is going up. So then it's positive. So I add positive I2 R4. And now I'm continuing this way. Now this, notice this is I3 now. I3 going this way, but go from positive to negative for battery. So that's a minus. So I have a minus 3 right there. I'm going this way. My current I3 is going to the left, and my loop is also going to the left. So that's a minus. So minus I3 times R3 equal to 0. So what did I use? I used convention for V across R if it's positive, if the loop direction is opposite to the current, assumed current direction. So I assume this I1, I2, I3 is going in this direction, right? So in the end, your results may not be actually going in this direction. If it come out to be negative, then it means the current should actually be going the other direction. But in any case, for the convention, when I using the, for example, I2, R4, because I2 is going up and loop is going down, so they are opposite, so then I need to use positive. So that's why I have a positive there, but the other R, I have minus, minus, minus. And for the battery, across battery, I will use positive when it's going from negative to positive, right? So for example, the 10 is a positive, and in the loop 1, the phi is negative, but in the loop 2, the phi is going this way, so clock to clockwise. So loop in the loop 2, for the V2 here is going from negative to positive. So loop 2, this one here, I need to use positive phi. And for the V3, because I'm going up this way, so it's going from positive to negative. So going from positive to negative means it need to be negative. Yeah, because it's not going from minus to plus, it's going from plus to minus. So then this has to be negative. So then this here, I will have a negative right there. Okay, number 9, when the EMF is in series, for example, like this. So epsilon 1, epsilon 2, they're in series. And in this case, I will add the two together. So epsilon 1 plus epsilon 2, if they have plus, minus, and then follow the same plus, minus. So I call that the same polarity. Okay? It may not be the best way of expressing this idea, but you know what I mean. So positive to minus, and this is again positive to minus. It's always this from positive to negative. You know, if you're choosing this current is going this way, then it's always going from negative to positive and negative to positive. And then you add them together. You add epsilon 1, epsilon 2 together. Now you have something like this. So you have current going this way. So you have positive to negative, but here is negative to positive. So in this case, the 20 is going from negative to positive. So that's adding, that's 20. So that will be 20. And then this is a positive to negative. So I have to minus 10. Okay. So in this case, one EFM is actually charging the other, which is the larger one, the 20 volts battery is charging the negative 10, the 10 volt battery. So what does that mean? It means that our current going in this direction means the electron flow is going in this direction, right? For the electron flow. So that means if I close a loop, right? So I'm bringing the electron from the positive back to the negative, right? So this one here like this, right? So the electron will be going this way. So it means the electron is going out this way and coming back and coming to this side here. So my electron is back to the negative terminal for this one. So the 10 volt battery is getting charged by the 20 volt battery. Okay, so we will continue. Continue the two EMF in parallel. So we have one EMF epsilon 1 and the other one epsilon 2, and they are in parallel. And the internal resistor is R1, and this one internal resistor is R2. So what is the equivalent circuit? So this is the equivalent circuit right here, equivalent. So meaning that if I need to replace this epsilon 1, epsilon 2 by 1, and that will be epsilon, and then I'll replace this 2 by the R, and this one's no change. So this is the equivalent circuit of this one. So if I look at this circuit here, and I look at from this point, to this point. And what is the voltage? The voltage is equal to epsilon 1, if I look at this segment here, epsilon 1 minus I1 R1. So I'll be adding epsilon 1, then I will be reducing I1 R1. So this one here, the V of this side is larger than this side by how much? By this V here. So V is equal to epsilon 1 minus I1 R1. It's also equal to epsilon 2 minus I2 R2. So I'm writing that. And also you look at this one here, this point to this point, it will be equal to epsilon minus IR, right? So I is going this way here. So then this 3 is all having the common voltage. And then I'm now rewriting it in terms of I1 in terms of the rest of them. So I1 is on the left-hand side. And that will be, if you move this to the left, and then moving V to the right. So then epsilon 1 minus V, so right there. And then when you move it to the left, you divide it by the R1. So you divide by R1. So this side here becomes I1. So then you write this like that and like that. So you have three form. It's called 1, 2, 3. I'm going to put this 3 equation back into A. Then you will see I1 put in there, I2 put in there, I put in there. And then you write them out. It will be just like that. You can see V divided by R1 plus V divided by R2 is equal to V divided by R, which the V is common, so V can cancel out. If you look at this 2 circuit here, the resistor is only R1, the resistor is R2, and this one, the resistor is R. So similarly, this R is using this parallel resistors equivalent formula. So 1 over R equal to 1 over R1 plus 1 over R2. And now you're looking at this here, this one here, this term, and this term, and this term, right? And then divide by R1, R2, R3. You can see they will cancel out because what they have is just the V right there. That's all, right? The V is times V, and then V cancel out, and then the rest of them is 1 over R1, 1 over R2, and then 1 over R. And this is a negative sign, that doesn't matter. So then that will cancel out. So you will live with epsilon 1 divided by R1, which is this, plus epsilon 2 divided by R2, and then equal to epsilon divided by R. So that's your formula if you want to find the equivalent EMF, right? You can use this formula here. You want to find the equivalent resistor, you can use that formula there. So those are the 2 formulas you can use for the 2 EMF in parallel. Now, in a special case, if we make epsilon 1 equal to epsilon 2, let's say equal to 10 volts, and R1 equal to R2, let's say also equal to 10 ohms. Now, you can use this formula here to obtain the R equivalent resistance will be 5. And then you put all this number into this formula here. You will see 10 divided by 10 plus 10 divided by 10 equal to this one here, epsilon, we don't know. And then R is 5, so we put that there. So you can find out the epsilon is equal to 10 volts. So you can see that this epsilon, in this special case, is the same as epsilon 1, the same as epsilon 2. So in general, when you adding 2 EMF in parallel, you don't really change the EMF. The EMF will still remain the same, right? Of course, it will be a little different, but in general, that trend is correct. That adding 2 EMF in parallel do not change the epsilon. Okay, so EMF in parallel only increase the current. So originally you have I1, originally here you have I2. Now in the end you will get I, so then that's I1 plus I2. So you adding, you increasing by adding I1 and I2 together. In this case, when they are in series, right? Remember we have this here, sorry, like that, right? Epsilon 1, and then we have then, right? So same relationship, plus minus, plus minus. So then you have epsilon is equal to epsilon 1 plus epsilon 2, right? So this one will be just like this, and then plus minus, and this is called epsilon, right? And epsilon is just equal to epsilon 1 plus epsilon 2, right? So then when you put EMF in series, if you put it in such a way, then you will increase the EMF. But if you put it in parallel like that, then you will in general increasing the current. Okay, so that's important to notice the trend, right? And capacitors in series. So the equivalent capacitance will be equal to, in the form that's opposite of the resistors in series. So when we are in parallel, you add them together. When you are in series, you have the reciprocal, and then the sum of the reciprocal of the C1, C2, stuff like that. So that is the capacitors in series and in parallel. And you will need the Q is equal to CV from previous sections when you derive this type of formula. Number 15, the RC circuit. So we're looking at one special case when the R and C are in series. So this is just a special case of an RC circuit. So the important thing is that the R and C, so the V, the voltage across R and the voltage across C in this type of circuit is a time varying situation. And also the current that going through this will be also time varying. So the time varying current through the RC also is a function of time, is a function of time, is a function of time. So you are looking at transient. Transient in Chinese is 瞬间, right? 瞬时的, 瞬间. Right? So we're not just looking at steady state. We're also looking at the steady state, meaning that at time approaching infinity, right? This means time is approaching infinity. So this is 稳态 in Chinese. 稳定的稳，稳态 and 瞬间. Okay, so now if you look at from the derivation, right? So you need to use the integral and calculus. Then you can derive VC. So the voltage across C will be equal to epsilon, which is this one here, and then the parenthesis 1 minus that. So this is an exponential decay function. So like we talk about here, this is exponential decay. So meaning as the time goes by, this value here will become smaller and smaller in a fashion that's exponential. So it will decay pretty fast. Depends on your tau, of course. So that's an exponential decay. So you can see there's a 1 minus exponential decay. So for VC, in the beginning, it's the highest value, right? Because when you put t equal to 0, that is 1. So t equal to 0, this is 1. So 1 minus 1 is 0. So then for the VC, it's starting from the 0 here. And then in the end, there will be more and more voltage across capacitor. Eventually, it would approach epsilon, right? So this value there is epsilon right there. So basically, in the end, this one here would be epsilon, and this one would have no voltage across it. So you can see I also draw the V across R. So in the beginning, it's epsilon right here, but in the steady state, this one would become 0. So it goes exponential decay to 0. But if you add these two together, VC and VR, they always equal to epsilon, right? So this plus this, according to Kirchhoff rule, the loop rule, you can see epsilon minus VC minus VR is equal to 0, right? So that's why this is true. And now if you look into the Q is also equal to 1 minus exponential decay. And this tau here that I wrote is actually equal to the R and C. So R and C value. And the units for that is tau is in second because it's the time constant. And so interesting that omega, right? Omega and the farad together, when you times them together, actually that will become the time in unit. You can actually show that. All right. So, and Q0 is the beginning value, right? No, actually it's in the ending value, right? So in the beginning you have 0. So when you first, initially this is initially uncharged. And then you have a switch there, you close it, so now you are closed loop now. So in the beginning, there's no Q. Q is equal to 0 right there. And then in the end, it will approaching this Q0 value. And this Q0 will be equal to C times epsilon, right? Using this formula there, right? So that is what the Q0 is. And how about for I? I is the exponential decay, right? There's no 1 minus. So you can see at a time equal to tau, you will have 0.37. So you'll be just like E minus 1, right? So just right there, E minus 1, T equal to tau. So T equal to tau is E minus tau over tau, right? So that's equal to E minus 1, which is equal to 0.37, right? And then times epsilon divided by R. So this, see right there, this is 0.37 epsilon divided by R when time is equal to tau. And time is equal to 2 tau, you can do the similar things, then you will find your value right there, which will be E minus 2 and then epsilon R, right? So then depends on what's E minus 2, you can go find that out. All right, so that is the exponential decay for the charging case. Now for the discharging case, now you have no, you will remove your battery, right? So no battery here, battery is gone because now your capacitor is fully charged in the beginning. Your capacitor is fully charged in the beginning, right? So that's why you have this V across C at the highest value in the beginning, right? Instead of, in this case, it started with a 0 in the beginning, meaning that in the charging case, this one here is initially uncharged, right? Uncharged initially. In the charging case, initially uncharged. Uncharged initially, right? And this one's initially fully charged. So then it will decay exponentially like that, okay? And so you still have the same fashion. This is tau, and then this one here will be 0.37 V0, right? Okay, same thing here. This one here will be tau, and that will be 0.37 Q0, okay? All right, so that's the charging case. Basically, you would start it, so you close the switch, and then the charge on the C negative plate. So in this case, the electron will start moving, right, toward this side here and come to this side to neutralize it. So more and more, this capacitor will become less and less charged. So that's what it does. It eventually becomes 0 when the time approaches infinity. Okay, and you're losing your Q, so you're losing Q until in the very end, T equal to infinity, you're approaching 0. So there will be no more charge here. Okay, and then there will be no current either too. So current will just decay like that too. Okay, so in the beginning you have current, and in the end you have no more current. Okay, so it's a transient situation. All right, so that's that part there. Ammeter. Ammeter in Chinese is called 电流计. And the objective is to measure the currents through this resistor. So there's a resistor here. Initially, you don't have this A connection. So you just have the epsilon and the R. So we want to measure what is the I through here. So the way you connect it, you connect this A, the ammeter, in series with the R. So why is that? Because A, the resistance of A is negligible. So when you put it there, it basically there's no voltage drop here. So the V drop through the A, it's close to 0. So you have minimum interference to the original circuit. So that's important because you don't want to, when you measure the V, and when you measure the I across through the R, you don't really want to interfere with the original circuit so that you can measure this value I more accurately, right? Okay, so in the case of voltmeter, in Chinese it's called 电压计. So the objective is to measure the V across, right? So we are doing across right there, across the R. So the way we connect it, we'll connect in parallel, right? So when we connect them in parallel, and because the resistance of this V is almost infinity, right? Approaching infinity. So if this is infinity resistance, when the current comes here, it will just kind of, everything just goes this way, and there's no current going that way at all, right? So that will be 0. Well, why am I drawing this way, right? It should be this way here, okay? It'll be going this way. So that will be 0. So nothing going this way, that will be equal to 0. The I into the V into the voltmeter will be 0. So then everything will go through here. So, but you still can measure the V even though there's almost no current. You just have a little bit, and that's enough to measure the voltage across the R. So that's the idea. You are not drawing current into the V from the regional circuit. So that's how you measure the V and the I using ammeter and the voltmeter. Okay. All right. So that's all we have for the DC circuit review. Hopefully you're learning more about the DC circuit and how you're using Kirchhoff rule, and in parallel, in series for the R and C and exponential decay. In the end, we have the ammeter and voltmeter. Okay, keep learning physics. Bye-bye.